Okay, let's dive in. We got a whole bunch of sources from you about something called liquid neural networks.
Hmm.
Sounds, well, pretty intriguing.
Yeah, definitely a bit different.
And it feels like it's pushing against some of the really big trends we see in AI right now.
It absolutely is. I mean, today's AI scene is just dominated by these massive static models, right? Like
Right.
transformers.
Huge data sets, learn everything, then deploy. Fixed.
Exactly. They're amazing for patterns in data that doesn't change, but, well, the real world isn't like that.
No, it's messy, constantly shifting, things happening all the time.
Precisely. And that dynamic, messy reality is where these liquid neural networks, LNNs, are designed to play. They're built for uh, robustness, being easier to understand, and efficiency, especially when things are unpredictable.
Liquid, because they adapt. Like water filling a container. Is that just a metaphor or?
It's actually more than just a metaphor. It's baked into how they work mathematically. They use continuous time dynamics, that's the math part, using things called ordinary differential equations, ODEs, and they have these really neat adaptable time constants inside their neurons. That's the core of the adaptation.
So it's not just a catchy name, it's fundamental. And the original spark came from a worm. Seriously.
Yeah, C. elegans, tiny worm, only 302 neurons, but it manages surprisingly complex behaviors.
Ah.
That whole idea, complexity from simplicity, was a big inspiration. Trying to build AI with, like, fewer but richer nodes.
Fewer nodes, but each one doing more, being more capable. It feels like that connects to other things we've talked about,
Right.
Thinking beyond just massive models and that neuromorphic hardware angle too.
Yeah, it really does seem to bridge those ideas. LNNs offer a different sort of philosophy for building AI, one that might just be a better fit for certain real-world jobs where the standard models, well, they struggle.
Okay, so that's our mission here. Let's get under the hood. How do these things actually tick? What's the math feel like, the architecture? And, the big question,
Mm-hmm.
why should we care?
What's the so what compared to Transformers and everything else?
Exactly. We want to give you a shortcut to understanding this area because it sounds like it could be pretty important.
Right. So let's maybe start with that core idea, continuous time, and the language used to describe it.
The language of change sounds dramatic.
Huh. Well, it kind of is. The foundation is ordinary differential equations, ODEs.
Okay, ODEs, remind me.
Think of them simply as math that describes how things change smoothly, continuously over time. So instead of a neuron's state jumping from value A to value B at discrete moments.
Like in a standard RNN or something.
Exactly. In an LNN, the state evolves smoothly. It traces a continuous path, a trajectory.
So its internal state isn't just a snapshot, it's more like a flow, a history built in.
That's a great way to put it. The interaction between neurons, how signals move, how states change, it's all described by these continuous ODEs.
And this continuous nature, it must have real benefits for dealing with, well, real-world data, right? It's not always neat and tidy.
Oh, absolutely. That's a huge advantage. Think about sensor readings or patient data from a hospital. It often comes in irregularly.
Yeah, not at perfect 1-second intervals.
Right. Traditional models need fixed time steps, but ODEs describe the system continuously. So the tools used to solve them, the ODE solvers, can figure out the network's state at any point in time, any arbitrary moment.
Okay, that sounds incredibly useful. Makes them naturally suited for messy, asynchronous data streams.
Spot on. Think industrial sensors, real-time healthcare monitoring, anything where the timing isn't perfectly controlled.
So that's the continuous time part. Now, you mentioned these adaptable time constants. That's where the liquid comes in.
This is where it gets really cool, yeah. In dynamic systems, a time constant, usually written as tau, tells you how fast the system reacts.
Okay, small tau, fast reaction, large tau, slow reaction, integrates more.
Exactly. But here's the twist in LNNs. These TARIAs aren't fixed. They're not just set during training and then locked.
They change.
They change dynamically, they're input dependent, they adjust based on the data the network is seeing right now.
Wait, hold on. The network can literally change its own, internal clock speed or attention span based on what's coming in.
That's the core idea. It adjusts the connection strength based on new stimuli after training is done. By tweaking tau on the fly, a neuron can decide react fast to this new thing, small tau, or integrate it more slowly into its longer-term understanding, large tau.
It sounds like a form of attention, but built right into the neuron's timing, not as a separate mechanism like in Transformers.
It's a really good analogy. It's an implicit attention over time embedded in the dynamics.
And this ability to sort of shift gears on the fly, that must be key for dealing with unpredictable situations.
Absolutely essential. If the pattern in the data changes, the LNN can adjust its parameters, its tariffs, to stay effective. That's why you see sources saying they can continuously adapt and reorganize, maintaining performance even when things get messy.
Okay, makes sense.
Mm-hmm.
But constant change,
Yeah.
does that make them unstable? Sources also mention stability and boundedness.
That's critical, especially for real-world use. You can't have an AI controlling something important go haywire.
Right.
The ODE structure itself, plus specific design choices like certain biases, help ensure the internal states don't explode or collapse. They stay within reasonable, bounded limits. You need that stability for trust.
So the math gives you both the flexibility and the guardrails.
Yeah.
Now, you said LNNs are a family, not just one thing.
That's right. Like with any evolving tech, different flavors have emerged.
Okay, walk us through the main ones, the family tree.
So the foundation, the originals, are the liquid time constant networks, LTCs. These directly use the ODEs with those adaptive liquid time constants we just talked about.
The pure form, basically.
Pretty much, they capture that core dynamic behavior.
But
But
there's always a but.
solving those ODEs step by step numerically during inference when the network is actually running can be slow, computationally heavy,
Practicality bites.
which led to the development of closed-form continuous time networks, CFCs.
Closed form, meaning you have like a direct equation, no slow step-by-step solving.
Exactly. The goal was to find, or approximate really well, a direct mathematical solution to the ODEs. This means you can bypass the slow numerical solvers when you run the network.
And that makes them faster.
Dramatically faster. Sources talk about 1 to 5 orders of magnitude speed up.
Wow, that's huge. What's the trade-off? Accuracy.
Remarkably little, apparently. Some reports mention less than a 2% accuracy drop compared to the original LTCs on common tasks.
Okay, that sounds like a very worthwhile trade-off for most applications. Massive speed for a tiny accuracy dip.
Definitely makes LNNs much more practical for real-time use or larger scale problems.
So we have the original dynamics, LTCs, and the fast practical version, CFCs. Is there a third branch?
Yep. Neural circuit policies, NCPs. Think of these less as a single neuron type and more as an architectural approach.
How you build things using the others.
Right. NCPs often use LTC, or more likely now, CFC units as building blocks. But they arrange them in a structured way, often inspired by biological circuits again, think C. elegans.
Okay.
And a key feature is often sparsity. Not every neuron is connected to every other neuron.
More like a real brain circuit. What's the point in NCPs?
The idea is to build systems that are potentially more interpretable because of that structure and also more efficient, partly due to the sparsity. They're particularly interesting for tasks like control systems in robotics.
So putting it together, LTCs are the core dynamic idea, CFCs make it run fast, and NCPs are a way to structure these units into larger, potentially more understandable and efficient systems.
That sums it up nicely, gives you options depending on what you need, fidelity, speed, structure.
Got the family dynamics.
Yeah.
How do they actually run and learn? Briefly.
Okay, the forward pass, getting an output. Inputs come in, they drive the changes in the internal states according to the ODEs. For LTCs, that means using a numerical solver.
Step-by-step simulation.
Right. Choice of solver matters there for speed and accuracy. For CFCs, it's much faster. You just compute the closed-form solution directly.
Learning. Still backpropagation.
Pretty much. Usually backpropagation through time, BPTT, similar to RNNs. But it's a bit tricky with continuous time.
How so?
For LTCs, you technically have to differentiate through the operations of the ODE solver itself. There are clever ways to do it, like something called the adjoint sensitivity method, which can save memory.
Okay.
But sometimes people might just use standard BPTT approaches because they want really precise gradients, even if it uses more memory. It's sort of a trade memory for numerical precision thing. Still an active research area, making training smooth and efficient.
Got it. Simulate or calculate the flow forward, backpropagate gradients through that flow to learn. Now, the big picture. How do LNNs stack up against the models everyone knows? Let's start with, say, LSTMs or GRUs.
Okay, traditional RNNs. Big difference. Continuous time in LNNs versus discrete steps in RNNs. And LNNs have those parameters, the time constants, that can keep adapting after training. RNN parameters are fixed once trained.
That adaptability again. Does that make them more efficient?
Often, yes. That fewer but richer nodes idea means they can sometimes achieve similar performance with fewer parameters. Plus, enhanced robustness to changes, and they have different issues with gradients, less prone to exploding gradients than simple RNNs, though vanishing gradients can still be a thing for long sequences.
Okay, different strengths there. Now, the heavyweight champ, transformers, How does this liquid approach compare?
Fundamentally different beasts. Transformers run on the attention mechanism, processing discrete tokens. LNNs run on ODEs, continuous processes.
Yeah.
Huge difference in complexity scaling. Transformers are typically 1n $2 with sequence length n because of attention. Every element attends to every
They're
other.
crazy expensive for long sequences.
Exactly. But CFC-based LNNs, they can achieve linear complexity burn-ins.
That's a massive advantage for things like processing long sensor streams or maybe even, I don't know, climate data.
Absolutely. And parameter efficiency, we touched on this, the difference can be staggering.
Give me an example again.
Okay, one source mentioned Stay LTC for predicting hospital length of stay. It used around 100,000 parameters. A comparable transformer could easily be in the billions.
Billions versus 100,000. That's mind-boggling.
Or another example, a tiny LNN, like 19 neurons, matching complex systems with over 100,000 standard neurons for certain self-driving tasks.
Fewer, richer nodes indeed. What else? Robustness.
Big point. LNNs are inherently designed to handle drift and noise because they adapt. Transformers trained on one dataset can be brittle if the real-world data shifts.
Makes sense.
LNNs handle time naturally continuous, irregular, no need for tokenization or complex positional encodings like Transformers need for time series. And training can often be cheaper, smaller models, different compute.
And interpretability. Transformers are famously black boxes.
LNNs, especially those NCPs with their brain-inspired sparse structures, offer potential for better interpretability. You might actually be able to trace signals through the circuit.
So it's not really LNNs versus Transformers across the board.
Not at all. Different tools for different jobs. LNNs seem really promising for dynamic systems control, edge devices where efficiency and adaptation matter. Transformers excel at large, static datasets, language, vision, where you can pre-train on the planet's worth of data.
Okay, one more comparison. Neural ODs. Nodes. They also use ODs, right? What's the difference?
Good question. Yes, shared foundation and ODEs. But LNNs, especially the original LTCs, are generally seen as, let's say, souped-up NODEs.
Enhanced.
Yeah, they have more expressive power because of those liquid time constants and how the neurons are coupled. Plus, LNNs often have that built-in focus on stability and boundedness, which isn't always the primary concern in basic node research. They offer, as one source put it, superior expressivity within the node family, along with that stability.
So, same core idea, but LNNs add specific ingredients for more power and reliability in certain contexts. It really does sound like a distinct approach to AI.
It feels like it. And that leads us neatly into summing up their core strengths, the liquid advantage, if you will.
Okay, let's hear the highlights.
All right. Number 1, robustness and generalizability. Handling messy, changing out-of-distribution data, super important.
Check.
2, computational and parameter efficiency. Fewer parameters, often less compute, especially CFCs. Big win for edge AI.
Got it.
3, enhanced interpretability. That potential, especially with NCPs, to be less of a black box.
Potential. Okay.
4, adaptability and continuous learning, adjusting on the fly via liquid time constants.
The core idea.
5, native handling of time series data, built for continuous, irregular streams, no awkward preprocessing.
Crucial for many real-world signals.
And 6, bounded nature and state stability, reliability for critical application.
And these all seem linked, right?
Mhm.
Stemming from using continuous dynamics and those adaptive constants.
Exactly. It's a coherent package deal stemming from that core philosophy.
There's always a catch, or at least some challenges.
Mhm.
What are the rapids LNNs are still navigating?
Fair question. Like other recurrent models, they can still struggle with vanishing gradients on really long sequences. Exploding gradients, not so much, but vanishing, yeah.
Right.
Training them can be tricky. Tuning the hyperparameters for those dynamic parts needs some know-how. And for the original LTCs, you're still somewhat dependent on good ODE solvers, though CFCs help massively during inference.
So that perception that they were slow is mostly history now because of CFCs.
Largely, yes.
Yeah.
CFCs were a huge leap in practicality. There's also ongoing work to see how well they generalize beyond just time series data. And let's be honest, compared to transformers with decades of research and massive industry backing.
LNNs are still the newer kid on the block.
Right. Fewer established best practices, fewer off-the-shelf tools, less community knowledge overall, standard growing pains for a promising but younger tech.
Makes sense? And what about pushing the boundaries? What advanced stuff is still under development?
Oh, lots of cool directions. True zero-shot learning. How do you get them to generalize to totally unseen tasks?
Yeah.
Distributed LNNs may be using NCPs and federated learning setups,
Interesting.
fusing different types of data vision, sound, sensors within these dynamic systems, squeezing out every last bit of latency for super fast control, adding reliable uncertainty quantification, making the network know when it doesn't know.
That's critical for trust.
Definitely. And just scaling them up, could we eventually see liquid foundation models? Big open questions.
You mentioned interpretability as a strength, but also a potential one. Is it always easy to see what's going on inside?
Yeah, it's nuanced. The structure of NCPs definitely helps understand the high-level flow, but the system is dynamic, meaning the internal states are constantly evolving according to those ODEs. Pinpointing exactly why a neuron's state changed in a specific way at a specific moment can still be really complex. The very liquidity that gives them power also makes detailed analysis tricky. You need specialized tools to really unpack it.
So promising for interpretability, but not a magic bullet. The dynamic nature adds its own layer of complexity to understanding it.
Exactly. It's an active area, developing those analysis tools.
Okay, let's shift gears slightly. Hardware. Neuromorphic chips, you said LNNs are a good fit. Why is that synergy so strong?
It's a beautiful match, really. Neuromorphic chips are designed to mimic brains massively parallel, often event-driven, super energy efficient.
Okay.
LNNs tick all those boxes. They're bio-inspired. Their continuous time nature maps really well to event-based processing, where you only compute when something significant changes.
So if the LNN state isn't changing much, the chip doesn't do much work?
Precisely. Sparsity, like in NCPs, is another thing neuromorphic hardware loves. And the overall efficiency of LNNs just complements the low-power goal of the hardware. It's like they were made for each other.
Event-driven hardware meets event-driven computation focus.
Yeah.
That could lead to some seriously efficient AI, right?
Ultra-efficient AI. That's the dream. Imagine running complex, adaptive AI real-time learning, handling tricky sensor data on tiny devices.
Edge devices, wearables, micro-robots.
Exactly. Places where power and latency are super constrained. We're seeing examples already, like LNNs on Intel's Lowy 2 chip, showing massive throughput gains and energy savings compared to standard hardware for specific tasks. It's efficient hardware plus adaptive algorithms.
That really could open up AI applications that are just impossible today because they drain a battery in seconds or take too long to react.
Absolutely. It's pushing AI out of the data center and into the physical world in a much more integrated way.
So looking forward, where do LNNs seem poised to make the biggest splash? What applications scream liquid neural network?
Anywhere with those dynamic, continuous data streams, often needing efficiency or robustness. Telecommunications is huge. Think future 6G networks that need to constantly optimize themselves, handle vehicle-to-everything communication.
Dynamic networks managing dynamic connection.
Exactly. Healthcare, obviously. Real-time patient monitoring, digging through messy electronic health records, predicting outcomes like length of stay. That StayLTC example is key there.
Monitoring complex biological systems that are always changing.
Precisely. Then you have autonomous systems, drones, cars, robots. They need to navigate unpredictable environments, react instantly. LNN's robustness is perfect there.
Makes sense.
And just general edge AI and IoT, putting more intelligence directly onto small devices, even finance maybe, modeling fast-changing markets.
The common thread is always that time-varying, often messy, continuous data stream.
That's their sweet spot. And beyond specific apps, they feel like a piece of the puzzle for next-gen AI generally.
How so? Addressing bigger AI challenges.
Yeah, like AI's brittleness problem, how models fail when data drifts. LNN's adaptation is a direct answer. The black box issue NCPs offer a path towards more interpretable systems. And moving beyond train once, deploy forever towards truly continuous lifelong learning.
Systems that can learn after they're deployed.
Exactly. It's a different paradigm.
We touched on open research questions like ZSL, distributed LNNs, multimodality. These sound like fundamental AI goals, not just LNN-specific ones.
They absolutely are. But LNNs offer this unique, continuous time dynamic perspective for tackling them. It's a different angle that might unlock solutions static or discrete models can't easily reach.
So wrapping it up, LNNs bring this blend of adaptability, robustness, efficiency, potential interpretability, all flowing from that core idea inspired by biology, using ODEs and especially those liquid time constants.
It really is a conceptual shift, isn't it? Moving from AI as static pattern analysis to AI as a continuous, adaptive interaction with the world. Not just systems that know stuff from the past.
The systems that can continuously learn and become based on ongoing experience.
That's the potential.
The fascinating case where the code, the math, the architecture really enables a different kind of cosmos, a different potential for how AI operates in reality.
Yeah, and it leaves you thinking, doesn't it? What changes when AI systems aren't just analyzing the world from outside, but can actually truly live and adapt within it alongside us? What kind of AI does that enable? And, well, what does that mean for our relationship with it?